Hey guys, today we're going to start our new unit, which is going to cover both Newton's third law and also momentum. But today we're just going to be dealing with Newton's third law of motion, which is the law of action and reaction. And you've probably heard this before, very famous quote, for every action, there's an equal and opposite reaction. But I kind of don't like that. Yeah, the example he often gives is rockets. That's, hey, this is why rockets are able to fly in space. And they never really explain why, but hey, what are you going to do? Anyway, I kind of don't like this one. It makes sense if you understand the third law, but I vastly prefer to call the third law the law of paired forces. The law of paired forces. So write that one down, and we'll move from there. Okay, what do I mean by the law of paired forces? This is again kind of falls into the category of natural philosophy as far as what Newton came up with. This is a general rule about how the universe works. It's not something that we can hang numbers on so much. It's mostly an observation of how our universe works. That said, it is the most far reaching and gives us the most insight into how systems are operating and interacting with themselves and with each other. So the third law is a big one. Okay, so first off, forces always come in pairs. What do we mean by this? So your Chromebook, as you're watching this right now, is sitting on the desk, and your Chromebook is pushing downward on the desk. But at the same time, the desk is pushing up on the Chromebook. So the force that the Chromebook is exerting on the table isn't just one force by itself. It comes with another force, which is the desk pushing back. If a bat hits a ball in a baseball game, the bat exerts a force on the ball and sends the ball over the fence. But at the same time, the ball is exerting a force on the bat, and it may break the bat or put a dent in the bat if you're hitting a rock instead of a baseball. So anytime there's a force, there's always a second force that exists at the same time. Forces always come in pairs. Now, second, the two forces always act on two different objects. So to go back to that baseball and bat example again, the two objects are the baseball and the bat. Um, the bat pushes on the ball pushes on the bat. Third, the paired forces are always equal in magnitude and opposite in direction. So the bat is pushing the ball toward the fence for the home run, but the ball is pushing the bat backwards, back toward the batter, back toward the catcher, maybe a better way to say it. So uh, another example is again with you, the Chromebook and the desk. The Chromebook is pushing down on the desk, and the desk is pushing upward on the Chromebook. So the directions of the two forces are exactly opposite, but the forces, the magnitude of the forces, are equal. If the Chromebook is pushing downward the force of 20 newtons, then the desk is pushing upward on the Chromebook with the force of 20 newtons. Yeah, so we're going to bring all these together. And finally, the two forces are always the same type. Okay, always the same type. What do we mean by this? Well, we have to do a quick review of the two types of forces, which I think we've talked about before. But there's contact forces, which are occur only when the two objects are in physical contact with each other. So the baseball and the bat, that's a contact force. There's no force between the bat and the ball until the bat actually hits the ball. Then there's a contact force when they're in contact and the force exists. So pushes and pulls between solid objects, tension in a string, pulling on something, that's another type of contact force. It's also the tension exists between the fibers within the string or the rope. And finally, friction, when you're trying to slide something across a surface. The friction only exists when the two objects are actually in contact with each other. Okay, the other types of forces are field forces. These are forces that exist at a distance. So like magnetism, gravity, and static electricity. Those are all field forces. So a magnet exerts a force on another magnet or on a piece of steel, even if the magnet is not touching the metal. Gravity exerts a force. The earth exerts a force on you even when you jump up off the ground and you're not physically touching the earth. The gravitational field of the earth is still exerting a force on you. So contact forces and field forces. And what this last bullet says is the two forces are always the same type. So for the baseball hitting the bat, that's a contact force. There's a contact force between the ball and the bat, and between the bat and the ball. If you have a magnet pulling on a piece of metal, the metal is pulled toward the magnet, but at the same time, the magnet is pulled toward the metal. And it doesn't matter if they're touching or not, but the type of the force between those two is always the same. Magnetism in the case of magnets, contact force in the case of the ball and bat. And that's true of any type of force in any pair of objects. Okay, so this is the way we kind of sum it up here. This is the this is the phrasing that they use in the book, and it's pretty darn good. If object A exerts a force on object B, then B exerts the same type of force on object A and with the same strength, but in the opposite direction. So that is a rephrasing of the famous for every action there's an equal and opposite reaction. And if you squint just right, you can see all that stuff in this phrase here. For every action there's an equal and opposite reaction. But the spelling it out in greater detail is much better. So there it is again. Object A exerts a force on object B, then B exerts a force on object A with the same strength, but in the opposite direction. Now, I listed all these things. These are the four characteristics of pairs of forces according to the third law. Now, if you can identify a pair of forces that satisfy all of these requirements, then we call this an action-reaction pair. So it's a pair of forces which form an action and a reaction. Okay? Every force is always part of an action-reaction pair. That's another way to say the third law. You cannot have a single force in isolation. It is always part of an action-reaction pair. And when we figure out and can identify the two parts of the action-reaction pair, sometimes we can realize things that we never knew before. Okay, so this slide here is an important one. I want you to pause it here and make sure you have all this information down in your notes because this summarizes it very well. These are the four requirements of the third law. And if you can identify a pair of forces that satisfy all these requirements, then we call that an action-reaction pair of forces. Or a pair of objects, which is exerting an action-reaction pair of forces on each other. Okay, now how can we, let's see, this is another summary of the same thing. You may like this one better. Newton's third law says you always have two forces. The two objects influence each other, and the two forces are of the same type, and the forces are always equal in magnitude and opposite in direction. So for example, if a car crashes into a tree, obviously the car is exerting a force on the tree. The tree shakes and leaves fall. But at the same time, the tree is exerting a force on the car, which may not be immediately obvious, but when you think about it for a moment, it has to be true. Because otherwise, what would be bashing in the front of the car? What would be making the huge dent on the front of the car? It required some huge force. And that force was exerted by the tree on the car when the car hit the tree. So we have two forces, the car pushing on the tree and the tree pushing on the car. We have two objects, in this case, the car and the tree. The two forces are the same type. It's a contact force of a push of the two objects pushing on each other. And the two forces are equal in magnitude, but opposite in direction. The car is trying to push the tree over to our left. The tree is bashing in the front of the car to our right, or stopping the car, pushing the car to the right. So when the car was moving to our left, the force of the tree stopped it, which means it's force acting to the right. Okay, let's see if we can apply this in a couple ways now. So here's an airplane. And as you know, an airplane is a propeller-driven airplane is driven by a propeller, which is basically a giant fan which blows air toward the tail of the airplane. And in so doing, it drags the airplane forward through the air. So if we were looking at the propeller blades, the individual propeller blades, the question here is, which way will do the propeller blades bend as the airplane is flying along? And you have three choices. It could be the red one, which is no bend at all. The blades are just pointing straight up. Or it could be that the blades bend forward a little bit in the direction that the airplane is flying. Or the third choice is that the blades bend backwards toward the tail a little bit. Now, for this example, we have the gas pedal pushed to the floor, if you will, the throttle lever, the power level pushed all the way forward. So the engine is producing as much power as it can. The propeller is dragging the airplane through the air with as much force as it possibly can. So I want you to pause the video here a little bit and think about this and see if you can answer the question. Which way does the propeller bend? Does it bend forward? Does it bend backwards? Or does it not bend at all? Okay, the answer here. I'm going to talk you through this, and feel free to pause it at any time to think about it a little bit more to see if you can see where I'm going with this. All right, so the propeller is exerting a force on the air. It is pushing the air backwards toward the tail of the airplane. As we said, it's like a fan blowing the air backwards toward the tail of the airplane. So that means that the blade is pushing on the air and pushing the air backwards. Now, third law says that if the blade is pushing on the air, that means that the air has to be pushing on the blade, which means that the air is pushing the blade forward. And the blade actually bends forward a little bit as the airplane is flying along. A little counterintuitive, but that's the way it is. And here's a little proof for you. These are pictures of airplanes which have crash landed. Well, not really crash landed. They've landed with the landing gear up. These both look totally survivable, like the people just walked away from them. But you'll notice that the propeller blades are bent forward. Here's one these two are bent forward, and then this one here, this one is also bent forward. Now this one is bent backwards. We'll get to that in a moment. But this blade is bent forward, and this blade is bent forward. And the reason is because in both these cases, the engines were producing power when the airplane hit the ground. So when the blade hit the ground, it tried to throw a chunk of dirt backwards towards toward the tail of the airplane. And since dirt is much denser than air, it had too much inertia and exerted a huge force on the blade, bending it forward. Now, what about this blade, which is bent backwards? Now, what happened here is that when these first couple blades hit the ground, it broke the propeller shaft. This is a very common thing in hard landings like this. It broke the propeller shaft. So by the time this blade came around and hit the ground, the engine wasn't producing power anymore. And then the blade was just dragging on the ground, and the blade pushed the dirt forward, and the dirt pushed the blade backward and bent it. Now, this is something that accident investigators look at when they look at the sites of plane crashes, because this tells them whether or not the engine was working when the plane hit the ground. These planes did not have engine failure, and they didn't run out of gas. Something else happened to cause them to hit the ground. Okay, now we have a worksheet here. I'm going to just show it here. This is posted in the assignment, and I want you guys to work on this. It's fairly self-explanatory. You're going to, these will become repetitive, but they're establishing a pattern, which is very important here. You'll see the pattern pretty fast. So the example is that the fist hits the wall. That is the action force. You're supposed to identify the reaction force, the other part of this action-reaction pair. And in this case, it's the wall hitting the fist. So the action force is the fist hits the wall, and it's a force acting to our right. The reaction force is the wall hitting the fist and pushing the fist back to our left. Second one, the head bumps the ball. The head pushes the ball up and to the right. The reaction force is the ball pushing the head. Ball bumps head and pushes the head down and to the left. And any of you who have ever headed a soccer ball know this is true. You hit the ball forward, but it knocks your head backward a little bit. I'll do one. Well, we already talked about this one. Bat hits the ball. That's the action force that's given, and it pushes the ball to our right. The reaction force is the ball hitting the bat and pushing the bat backward to our left. Do that for all of these, and then continue on here. There's also a graphic on the bottom on the worksheet that you have, and think about that a little bit. It involves a strong man playing a tug of war. We'll go over that in greater detail in class. Now, the front side of this worksheet establishes a pattern that you want to use on the back side. Okay, I want you to go through this carefully. I can't do this on the recording. It requires more of a class discussion, but we'll go through this in class if you're confused on it. But it takes you through a thought process to make you realize something, help you realize something that you may not have ever thought of before.